Hi, I'm Chechik. I'm a professor at Bar-Ilan University at the Computer Science Department, and I also had the Nvidia research group in Israel. And today, this morning, was mostly about generative AI in the context of text language. And I'm going to talk about the other side of generative AI. Hi, everyone. It's really fun to see so many familiar faces in the audience. So hi, everyone. Hi. So I'm going to talk about the other side, about generation of visual content. So just a few examples. How many of you have played with Midjourney or DALL-E or anything like that? How many of you have never, ever heard about it? Okay, good. So I'm sure you all know that we now have tools that can generate really high quality, fantastic images. Some of my favorites, someone took the Shirim Shel Shlomo Artzi and had based on excerpts from the songs like Chatulim Chashvim et Kitzam Le'achor. You could also have very realistic images, fantastic images, all very impressive. So I'm going to talk about this and about extensions to that. So first, I want to highlight that this is all based on foundation models like there is in text, right? So if you think about the classical machine learning workflow, in classical machine learning, you have your data, you collect and label your data, then you train your model on your data, and then you deploy and infer on your data. And in diffusion models, this is very different. You collect huge data set in a way that is task agnostic. You don't care about a specific task. You then train a representation, again, task agnostic, not for a specific task. Usually in a self-supervised way, contrastive learning. Some of you know that. And then once you learn this representation, you use it for different things. So foundation models in text are like predict the next word, and an application would be chatbot, right? And in vision, let me highlight two foundation models. One is called CLIP, and this is basically a representation of images and text. So the idea is that you find some embedding space, I don't know if you can see my pointer, a joint embedding space of words and images, and you take a large data set of 400 million images with their descriptions. And you just make sure you train a text encoder and an image encoder in a contrastive way such that, images would be located close to their text, to the description text. So that this is a model that is CLIP. We're going to use it later. It's really, really useful. Another model I want to talk about is this family of diffusion models. I'm sure you all heard about stability AI, stable diffusion. So again, this is trained on very large data set like Leon 5 billion images. And let me tell you in very shortly how this is actually done. And the idea is actually really, really simple, okay? You take images, and this is a nice kitten here, and you add some noise. And then you add more noise. And noise is just Gaussian independent noise per pixel. So you just repeatedly add more and more noise to your image. And is that more visible? So you add more noise to the image until at some point you get something that's completely noisy. Now you train a denoiser. You train a deep neural network that basically you sample one images across this continuum, let's say this pair, and you train the network to take a noisy version and denoise it a bit. And then again, you take another one and train to denoise it on a very large data set. And this way, the model basically learned that if you start with some random noise all the way to the right there, you repeatedly denoise and denoise and denoise. And at every time you also condition on the text, right? You say, this is a photo of a kitten. So you denoise a photo of a kitten, denoise a photo of a kitten, all the way to get really high, crisp, high quality vision images. That's the idea. It's actually pretty simple. Okay, so so I described to you kind of the state of the art in generating images, but the problem is that since all these models are trained on huge web data, they are not about your images, they are not about your visual content, right? So how can we generate something that is about your content? And there are many ways, many reasons you might want to do that. Let's say you want to, there are two sides here. There's analysis and synthesis, right? Let me talk about generation in a second, about synthesis in a second. But even in analysis, in image understanding, sometimes you want to understand things about your data. Let's say you want to do image retrieval of your images, right? You want to perhaps recognize your garment or something. Or you want to find a specific item in a video. Or if you have a smart device in your home, and at some point we're going to have smart devices, we're going to have them refer to our personal items because they are going to be items in our house. They are not, you know, make coffee in my favorite mug and not in everyone's mug, right? You want them to refer to specific instances. And back to generation. So on the left, meet my brave dog, Max. He's a very, he's a beautiful dog, not that smart. So, you know, today people can generate me an image of a dog in Times Square wearing sunglasses, but maybe I want to generate images of Max wearing sunglasses, right? This is for personal use. Think about businesses. You want to come up with an ad campaign. Let's say that you're making toys, this teddy bear. You want to make an ad campaign of that specific teddy bear. Let's make him a wizard or a superhero, etc. Right? Or maybe you're an internal designer. You have some furniture and you want to design your new house with the existing furniture. This, I don't know why you want to keep this sofa, but maybe you want to, right? So there are a lot of really, really good uses why you want to generate content conditioned on your personal data. So we presented about a month ago in ICLR a paper. This is a collaboration with Tel Aviv University, Rinon Gal, and the lab of Tani Cohen-Or and Amit Bernamo and a lot of other. And let me just show you the idea. The idea is that you take several samples, just a few samples of your personal object, your specific object, and you teach the model from now on, here's the new word in your language, right? We're going to call it S star because we're mathematicians, but you can call it whatever you want. And once you have that, we can now, and I'll explain to you how, use that S star in a sentence as if this is a normal, regular word. So you can say, give me an oil painting of S star, an app icon of S star. My favorite one is Elmo sitting in the same pose of S star. So it really captured the pose. And you probably noted that the head got broken off and is laying there. So when you ask for a crochet S star, it noted that the head is missing. There are a lot of other examples. This nice kitty allows you maybe to design product with that specific toy. Okay, so how do we do that? Oh, before we do how we do that, let me show you I think a really interesting thing this method does. And I told you we just teach a single word. So we did the following experiment. These are input samples. Focus on the right, this teapot. And here's what happened when we teach the model with just 3 to 5 images, and it can generate these 3 examples on the right when you tell it a photo of S star. And what I like about this example is that, you know, this is not the identical teapot, right? The patches are not exactly the same. The handle is black instead of yellow or whatever. But it really captures what, you know, like the essence of this teapot. And in fact, when you do an experiment with people, if you just show them this, you know, briefly, or you ask them about and they basically say the variability within the normal ones is about the same as the variability between the original images and the generated ones. So surprisingly, this model, even though it can only learn a single word is going to be a vector, just a single vector, you can represent very complicated visual information with that. And of course, if you just try to use text, if you just ask people, describe the teapot in language, and then you use standard, you can see this is a bit older work. This was with DALL-E 2 and LDM. but anyways, whatever language model, text to image model you use, you're going to get something that's not visually similar to the specific object that you have, because text and language are just not rich enough to describe the particular appearance of a visual object. So how do we do that? The idea is actually really, really simple. I told you about clip. So what we are basically doing, we are just learning we're just learning a new vector that represent the word. And in this case, we go over this, we say a photo of S. After you have a tokenizer, this new S star, it just mapped to some new vector. And this representation is learned such that when you do the diffusion process with the example personalized images, you generate something that is similar to the images. So it's really a simple optimization of just a single word. So optimizing just a single word has, it's great. It's just a very, very light model. There is another model, very famous, very useful, called Dream Booth, where they basically retrained the full diffusion model. And it works great. There is one caveat that then you have a model that weighs like 7 gigabytes, right? So imagine that you want to train many concepts, maybe 100 concepts. That's really hard to use. So one intuition would be, perhaps we can train the model, then you get more richness and more complexity. But maybe you don't need to train all parameters in the model. Maybe you can train just a small number of parameters, get more richness, but still be lightweight. And we published a paper in SIGGRAPH that's going to be presented this August. That's called Profusion, for personalized diffusion or something like that. And the idea is that we learn a low rank modification of some of the cross-attention maps. And the details are in the paper, but the key idea is that you can intervene in a very lightweight in the model and have a memory footprint, or like this footprint of just 100 kilobytes, and still have high quality images. So here are a few examples. This is the teddy bear that I showed you before. Once again, you show these images on the left, you teach it, oh, this is now called Teddy, and now just generate for me an image like a Teddy dressed like a wizard, and it generates that. You can actually train two different concepts now because it's lightweight, and you can combine them, right? You have the Teddy sailing in a teapot in a lake, and they combine it in a nice way. And of course, finally, last example here is Max. I'm sure you saw this coming. These are images of Max, and now finally Max can read a book, and Max can cook a meal, painting of two Max on a boat, and a photo of Max wearing a hat. So, I mean, you guys, you don't know Max, but this is really my dog, okay? So I sent it to my family. They were really impressed that he reads books. So far, I told you about really personalization for specific instances, right? This specific Max. I want to tell you about a few other works that we submitted recently that I think will be interesting to you. And we looked at several problems that we still have with diffusion models. And here are a few. One issue is that on the left, let's say you tell the model, give me a yellow flamingo with a pink sunflower. These diffusion models, they don't parse correctly this matching between the noun and the attributes. So they just treat it kind of as a bag of words. And flamingo tends to be pink, so they make the flamingo pink and the sunflower yellow instead of the other way around, right? So this is the incorrect colors for a yellow flamingo. Another issue, and this is, these models were trained on web data. These models were trained on web data, and some of the words or some of the terms we have are pretty rare. Maybe they appear just a few 100,000 times or maybe tens of thousands of times. And usually when you try to generate, and here you have an example, a photo of a payphone, you get something like that, which is not a payphone. And on the right, maybe the most infamous problem with diffusion models, they are really bad with fingers, right? This is Yeah, right. I mean, the funniest thing I should find is at some point I did see an image of like a perfect hand with 5 fingers. Can you guess what the prompt was? Yes, a hand missing 1 finger. Yeah. So I'm going to tell you about some attempts to address these. So first, this is a paper we just submitted. It's going to be on arXiv very, very soon. So, you know, very, very hot. This is our solution to the problem. Here you do get a yellow flamingo with a pink sunflower, and you can do much more complicated prompts, you know, checkered ball with rustic wooden table or horned lion. So you could really have complex attributes, and our method can correctly assign them to the right noun. And the idea is actually really, really simple. You use the structure of the prompt, right? You can parse it and find the matching, right? If you have a red crown and a golden strawberry, you know that the crown should be red and the strawberry should be golden. And now you intervene with the cross-attention component of the diffusion model. And the cross-attention is something, it's really simple. For every word in a sentence, it tells you which pixels in the image should correspond to that word. So if you have red crown, what you want is that the pixels of red to overlap the pixels of crown. So we design a loss that does that. And it turns out that you don't need to retrain the model. You just, during inference, you do a denoising step, as I described to you, and then you fix a bit the cross-attention maps using the new loss. You do denoising and cross-attention maps, etc. So, and it turns out this is all you need. It works at inference time, and it really works well. Human evaluation experiment show it really works much better than every previous approach. Tons of examples. There are a few baselines, but I think in general, this idea of using the cross-attention component is the right way to combine this vision and language. And I think this is one of the few works that actually use the syntax of the prompt during inference. The next thing I want to tell you about is this problem that diffusion models being trained on web data, they are trained on really unbalanced data. So what I'm showing you here is, you know, that natural data is really unbalanced, right? There are some concepts that are really common, cats and dogs. Here, maybe gift and Jeep. And if you are at the head of the distribution, models generate things that are really, really fine. They look good. But if you go to the tail of the distribution, and you can actually check in the data set, right, in the Leon 5 billion data set, which items were common and which were rare, then you get these weird, you know, too many fingers or bad, this is not a payphone. And our approach succeeds to fix that. So let me tell you how. The intuition, okay, the question we ask ourselves is, okay, so it cannot generate payphone. Why is that? Maybe it saw so many cats and dogs, all the common concepts, that it completely washed out what is a payphone, right? It only saw that 10,000 times. But maybe on the other hand, maybe this information hides somewhere in the model, and you just need to extract these repressed memories, you know, hypnotize it and find the repressed memories of payphones. And so here was the intuition. I told you, how do you generate these images? You sample from the space of noise. This is a very high dimensional Gaussian noise, 64 plus 4. It's really high dimensional. And if you trained using cats and dogs, you sample well all that space. But if you only had smaller number of samples, maybe you just sampled part of that space. And the idea was, let's find that part of space where the model can generate payphones. So I don't have a figure showing you the method, but basically you search in the noise space, given again few samples, so such that for an area that you can generate similar images. And now suddenly, yes, you can generate all the rare concepts. And we can use it now for many things. Basically, data augmentation. If you have an unbalanced data, you can just take just a few data samples and generate tons of data from that. Okay, and these are new, right? They're not just copies of the examples you have in the same way that the model generalized. And there are a few examples here of these oxygen masks and payphones. And using this, we actually get strong improvement in all over all state-of-the-art few-shot learning and long-tail learning. Okay, a few words about the future. I told you about images, and one thing that's really nice about vision that we are moving from images to vision, right? And vision is much more rich and complicated. It involves 3D data, like 3D models of things. It involves video and even agents that behave, right? We want to generate actually behaving agents. So these are a few examples from recent work. On the left, the 3D approach called Magic 3D. In the middle, again, another paper from Nvidia. And I want to tell you in a few words about the right side, which is a paper from our group, again, to be presented at SIGGRAPH. So the problem again is you want to generate, but not just generate a video of something. You actually want to generate a policy that controls an agent in an environment. Okay, so you generate a policy and then you let the agent just play in the environment and do what you want it to. So there are these two phases. Let me play the video for a second. Yeah, he looks very happy. So the point is that there are two different goals here that you try to balance. One is you want the agent to behave in a normal way, or like the way that a person does. For that, you personalize this by collecting some data using motion capture. But then you also want the agent to be directable, so you can give it text instructions and it will follow them to do some goals. So here is an example where you tell it move to the right, right, and hit this box and then celebrate. You see it's not very stable. Okay. And again, you take the motion capture data. This allows you to teach the kind of fine behavior, but you also train another component of the high-level policy that controls what it can do, right? You can tell it go there, go here, and perform tasks. Okay. Yay. Okay. So thank you so much. This work was in collaboration with so many collaborators. I mentioned the group at Tel Aviv University. This is also in collaboration with several groups at Bar Ilan University, my own group, and the group of Yoav Goldberg with several students, which are listed here. I don't have time to talk about. Some of the work was in collaboration with members of the Nvidia research group in Israel. And thank you so much.